This video brought to you by Lego Dog. Maybe German Shepherd? I don't know. Comes with the police sets. Okay, so we've seen a Pythagorean identity and how we used it, along with the basic identities, to simplify expressions. Really, I think what we should say is rewrite expressions in different forms. So now we're going to look at sum and difference identities. So remember that we can consider arc length and angle as equivalent. So provided we are measuring angles in radians, this means that any two real numbers can be thought of as both distances around the circle or angles. So with that idea, we can construct these new identities. Now, when we say construct, we say go look in the textbook and you can see a nice proof of where these came from. We're just going to give them to you and say, look, here they are, and here's how we can use them. Note that this is a little inconvenient for your understanding. There's 6 identities written here. So here's the first one. If we have sine of the sum of two angles, that's equal to sine of the first angle times cosine of the first angle plus cosine of the first angle times sine of the second angle. And then for the minuses, we cover up that. Minus goes with minus. With cosine, it's opposite. If we're adding two angles, then it's the difference of the products. If we're subtracting two angles, then it's the difference of the sums. And then for tangent, it's a little wonky of a thing. The numerator is a sum, the denominator is a subtraction for a sum, and then vice versa. Okay? So what we're going to do is use these to find exact trig function values. So for example, sine of 5 pi 12ths, we do not have an exact value for that. It's not in the unit circle. So if we type this in the calculator, we're not going to get an exact value. We're going to get an approximation. However, we can use one of these identities, actually just this one, because sine matches with sine, to write this in terms of, to write it as an exact value. Now, what we have to do is think of two angles in the unit circle that add up, or a difference of two angles that equals 5 pi 12ths. So I'm just over here going to state that 5 pi 12ths feels like it's equal to 2 pi 12ths plus 3 pi 12ths. That seems like a reasonable statement, right? Well, if I simplify 2 pi 12ths, I get pi 6ths. And if I simplify 3 pi 12ths, I get pi 4ths. Those are both unit circle values. So those are the ones we want to use. Meaning, I'm going to rewrite the sine of 5 pi 12ths as sine of pi 6ths plus pi 4ths. And then I'm going to apply my trig identity up here that says if we have the sum of two angles, we can rewrite it in this form. So here goes. This becomes sine of pi 6ths times cosine of pi 4ths plus cosine of pi 6ths times sine of pi 4ths. I'm just directly copying this down, and I'm putting in pi 6 for the first angle and pi 4 for the second angle. Now, going to my unit circle, which you have memorized by now, I'm sure. Let's see, we have cutting the circle, the half circle into sixths and then fourths. I know that this point here is root 3 over 2 comma 1/2. And I know that this one here is corresponding to pi fourths is square root of 2 over 2 comma root 2 over 2. And then I know if I put in the pi thirds one over here, it's just these two switched. So if this is pi 6ths, I know that sine of pi 6ths is equal to the y value in the unit circle. So sine of pi 6ths is just 1/2. Cosine of pi 4ths is the x value in the unit circle. So that would be root 2 over 2. And then plus, now cosine of pi 6ths is the x value. That's square root of 3 over 2. And sine is the y value from the unit circle, corresponding to that arc length or angle, whichever way you think about it. That's root 2 over 2. Okay, there it is. Now we just need to do a little bit of algebra to simplify this expression. Note that we can just multiply across for the fraction, so I get root 2 over 4 plus the square root of 6 over 4. And then we could rewrite that as the square root of 2 plus the square root of 6 all over 4. I'm not sure what MyMathLab is going to prefer here. There are other options. Note that the square root of 6 is the same thing as the square root of 2 times the square root of 3. So we could factor out a square root of 2, and we could rewrite this as root 2 plus the square root of 3, all that divided by 4. But I don't know that that's super useful. I think this is probably the best version of that answer. All right, well, let's do another. Oh, gross, degrees. I hate degrees. I shouldn't hate degrees. They're fine, right? They're just arbitrary, right? We made them up. Radians are not arbitrary. They're linked to something real. Okay, so cosine of 165 degrees. We need to write angles in the unit circle that add or subtract to 165. I think we kind of like values in the first quadrant. So if you think about that unit circle, the values in the first quadrant are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and then 90 degrees is not in the first quadrant. Neither is 0 degrees. They're quadrantial angles. So if we could find a way to rewrite this as a sum of these things, that would be awesome. Boy, it doesn't look like it's going to happen. How about this? If I kept going, the next in quadrant 2, we'd get 120. If I added 30 to that, and then if I add 30 to that, I get 150, and 30 to that gets us to 180, and there's another one in between here that's the 45. So if I add 45 to 90 degrees, I get 135 degrees. So we could do this as, let's see, we could do 120 degrees plus 45 degrees. We could do 135 degrees plus 30 degrees. Let's do that one. Why not? So we're going to rewrite this as cosine of 30 degrees plus 135. All right. That means using our identity here, since it's a sum, I probably should have done a different so you could see that, but whatever, it's all the same, right? We're going to do cosine of the first angle, so cosine of 30 degrees, times cosine of the second angle, cosine of 135 degrees. And then since it's a sum, we need to subtract the sine product. So minus sine of the first one, sine of the second one. Of course, you know that the order you multiply it doesn't matter. So had we switched these around in terms of cosine 135 first, it all would have been good. Okay, let's head off to our unit circle and see if we can't figure out what these values are. So I'm going to draw it. We just need the first and second quadrants. 30 degrees is here. That's the same as this one, that ordered pair, root 3 over 2 comma 1/2 for x and y. And then 135 is the 45 degree angle over here. So that's root 2 over 2 comma root 2 over 2. But notice the x-axis is negative, so we'd have a negative value there. All right, now we can fill in this mess. So cosine of 30 is root 3 over 2. Cosine of 135. Cosine of 135 is square root of 2 over 2, but it's an x value, so this is negative root 2 over 2. And we're subtracting. Sine of 30 is that positive 1/2. Sine of 135 is the positive root 2 over 2 because it's the y values. All right, all we got to do is multiply through and then do a little bit of arithmetic or simplifying of this. So let's see, this piece becomes negative square root of 6 over 4 minus square root of 2 over 4. So, you know, that's very similar to this previous one. That could be our final answer there. We could also write this as the negative square root of 6 minus the square root of 2 all over 4. That's probably the best one. We could factor out negative root 2 just like we did over here. And so we could write that as the square root of 3 plus 1 all over 4. Not super useful, honestly. Maybe. I don't know. Depends on what we need to do. We might be happy with this answer. You'll just have to double check what MyMathLab is requesting of you for an answer.